7.8 Using exponential and logarithm functions. So, in this lesson, it's all about solving application problems using logs and exponential functions. So let's get into it. So first, we have something called exponential growth and decay. Now we did a little bit of this before with the power functions, but now we're going to do it exponentially. So both of these I'll give you as always. If it's exponential growth, it's a basic formula that looks like this. Notice e to the x, I'm not sure we talked about this, and e to the x graph looks like this. Across that one, it's like a power function. Since e is 2.71, it consistently grows. It's a growth function. Now if I put a negative on top there for exponential decay, why is that decay? Because remember the negative's on the top, so it's a horizontal flip. So a normal graph looks kind of like this of an e graph. It's a horizontal flip, so it's going to be going like this. It's going to be decay function. Oh, it's not a very good graph, but that's the idea. So exponential decay, exponential growth. Now, a is initial as always. A is initial value. E is e. T is time. And k is what we call the growth rate or the decay rate. Rate of growth, rate of decay. So that's the general idea. If I use something like this, if it's an exponential graph, initial value, e is e, 2.71. K is the growth rate, and then T is time. Let's do a couple special problems like with this. First one, half-life of plutonium-239 is 24,000 years. Different value K. So a couple things going on with this. When they say half-life, that means how long till you get half of what you started, right? Half-life. So this is a decay function. So we're gonna start like this. Negatives is decay. Now, very importantly, it said half-life. So that means that, this is what's important about this, is that A is your initial amount. I want the half-life. I want how long it takes to get half of that. So this is actually my equation. Anytime they say half-life, this is your equation. Right? Because it doesn't matter what your initial amount is. At the end, you want half of that. And actually, what happens here is, well, if you notice, if you divide both sides by a, the a's cancel out. So actually, the equation just has to be this. That's a half-life equation. How long till you get half of your initial amount? Well, if you do that, a's cancel, you get this. And all we gotta do now is plug in our time, 24,000 years. So I'm gonna get 1/2 equals e to the negative k times 24,000. Remember the way you get rid of e? Take the natural log of both sides. Natural log of 1/2 equals negative 24,000 k divided by negative 24,000. And we're going to get our decay factor. And then all we do that, we just use our calculator. I turn it on, hate that. So natural log of 1/2, oops, not double natural log. Natural log of 1 divided by 2, close the parentheses, divided by negative 24,000. And I get, so what's this notation? That's exponential notation. See how it's 2.888? E to negative 5, that's like saying times 10 to the negative 5. So 2.8, it will do 2.89. Times 10 to the negative 5. That's what that was. That's exponential notation. So you could like that, or if you want, you can move it over 5 spots and get 0.0000289. That's the decay rate of plutonium. So that's how that works. Let's do another one. The half-life of potassium is about 1.5 billion years. I don't want to deal with that. So let's just skip that. It's 1.5 billion years. Let's do the next one. More interesting. A certain food is dropped on the floor and is grown bacteria exponentially according to the model y equals 2e to the kt, where t is time in seconds. This is the same word like I will give you. So here's an equation. Y equals 2e to the kt. T is second. This is the growth rate of bacteria, so bacteria grows. We start off with initially 2 cells initially. Oh, look what it says here. If there are 2 cells initially, hence the 2 right there, makes sense. and 8 cells after 20 seconds, find the value of k. So what's going on here? This is a point, right? You're plugging in time and you're getting the number of cells. So this is a point of, in seconds, 28. A little tricky, right? But look what it says, right? You have 2 cells initially, initial amount. You have 8 cells after 20 seconds. Now, 20 is time, so when they plug in 20 seconds, they get 8 cells. So let's use that as a point. So I get 8 cells when I plug in 20 seconds. So I get something like that. How do I solve this? Same way we always do. Isolate the e. So let's divide everything by 2. 4 equals e to the 20k. And then we have to get rid of the e, so we're going to take the natural log both sides. These would reduce. A natural log of 4 equals e to 20. Oof, e's out, sorry, 20k. Then you divide by 20. This is something for a calculator. So, natural log of 4, don't forget to close the parentheses, divided by 20. And roughly 0.0693. It's about 0.0693. So that's my k. That's the growth factor of this bacteria. So B here says the 5-second rule, we all know about that, says if a person who drops food on the floor eats it within 5 seconds, there should be no harm. How much bacteria is on the food after 5 seconds? Let's figure it out. Right, we have our equation now, right? This is what they start off with, but now I know what k is. So my equation is y equals 2e to the 0.09693 to 6, kind of hard to see, t, right? So that's my k. Now let's plug in 5 seconds. So y equals 2e to the 0.0693 times 5. Sounds like the job for a calculator. So 2 second e. Now I'm actually just going to use the answer I have up here. Like, look at all this. That's still in there, so I'm going to use that, times it by 5. And we get about 2.82 bacteria. And then C says, would you eat food that's been on 4 for 5 seconds? Why or why not? Based on this, it's not that much more bacteria, but again, that's kind of weird. It's kind of personal preference. Is this exercise reasonable? Probably not. There's lots of different types of food. How dirty is the floor? How bacteria? Lots of reasons. Anyways, let's move on. Logistic growth. Now, logistic growth is a type of growth where we actually start leveling out. So you have like a growth in population. And at some point, you kind of hit like the max value, and you start leveling out. So look, the reason we're doing logistic growth is because it's super important in the sense of it's probably the best way to represent population growth. Because we talked from all those old problems where I ask you, does it make sense to go on forever, grow forever, and the answer is always no. This takes care of that. Now, it makes sense it goes on forever because it's going to eventually level off. So that's what we use logistic growth for. So the best way to talk about this is look at the problem and look how it's represented. Let a and b be positive constants where b is less than 1. Logistic growth function is represented by f of t equals c over 1 plus e to negative bt. So a couple things here. E is the growth factor, is the limiting factor. Limiting factor. So that means that's the max. That's like your max. So right here, our max is going to be 118. So look at it and go, okay, that's my max. Not going to get higher than 118. And since it is a max limiting factor, it's also a horizontal asymptote. So horizontal asymptote is always going to be the c value. So y equals c. Okay. So, and then I should talk about a is kind of like your initial amount. That's a growth or decay factor depending on what we're talking about. So let's look at this one right here. It's a good example to do. The population of a certain species of fish in a lake after t years can be modeled by the function this. So again, now this is why we have to do a logistic function because it's to level off. The number of fish in a lake, that's not going to go on forever because the lake's only so big. You can have like a billion fish in there. At some point, the population is going to stabilize. So this problem wants me to do. It wants me to graph the function 0t to 500. So let's bring on my calculator. They want me to graph this. I'm going to go to y equals. Turn on my go to y equals. Now, I think we talked about this before. The easiest way to graph this ugly fraction is to put alpha y1, and it brings up this fraction thing there. So now you can type it in a lot easier instead of having to use parentheses everywhere. Type it in the way you see it. So 1800, 1 plus 1.42 e, so negative, no, negative, not minus sign, negative 0.037. Now we don't have an x, we don't have a t value in here, we're just going to use x. Right, so I have that, I get graph, and I see nothing. Because remember, my window's off. They want me to fix my x value from 0 to 500, so let's do that. Let's go to window, I want 0 to 500. I can hit graph. And I really still don't see anything. Why though? Because remember, what's my max? 1880. I'm not even close. I'm going negative 10 to 10. Let's fix that too. Let's go all the way up to, wow, I don't know why that happened. Let's go all the way up to about 2000, a little less, a little higher than 1880. And if I do that, I should be able to see it. And there you go, right? So it goes up, its population is growing. At some point, it hits that equilibrium, and it just starts like maxing out. So I could graph that function, put it there. Look something to this effect. What's the horizontal asymptote? It's always this thing. So y equals 1880. What's max population of the lake? Well, same thing, 1880 fish. When will the population reach 1880? Well, there's actually two ways to do this. One way is, well, let's set equals to that. 1875, I should set 1875 equals 1800 over 1 plus 1.42 e to the negative 0.37 something. Then I gotta solve this. Multiply both sides, blah, blah, blah. That takes forever. Let's do it with our calculator. We have it out. y1, y2. Or in our case, this is actually our y1 because we did this already. Let's put in y2 and see where they cross. Right? I already have this graph. Let's plug in this graph and see where they cross. So bring back my calculator. I'll go back to y equals. I'm gonna go to the second one now and put 1875. Make graph. There we go. So then they hit somewhere up there. So how do we find that? In our calculator, we go second, calculate intersection. Or you just gotta get close to it. Again, I don't know why it happens. I'll move a little closer to where it should hit. Hit enter a couple times. First curve, second curve, yes, guess, yes. And right there, about 169.6. So roughly, if we round it, 170 in 170 years. So 170 years, it should reach about a population of 1875. Let's do one more. Zoology. Suppose the red fox population in restricted habitat follows a function of this. So again, just looking at this, there's so much stuff I know, right? I know I started with about 18 something. I got the max population to be 1650. All that good stuff. So they want to graph the function, this function, from 0 to 200. So in our calculator, let's go back, let's delete some of this, and type in our new equation. Easier, delete. Okay, there we go. So this case, again, I'm going to do alpha y equals, make it a fraction, so it's so much easier to type in. 16,500. There we go, and then 1 plus 18 e to the negative 0.085. So it's all in there. Oh, don't forget my x. Okay, we can't do t, we just can use x. Now again, my window's a little off, because let me fix it. So on to stop it, and then I'm going to go to window. I should only go to 200 this time. And my max is going to be a little bit less. So it's 16,500. Let's go 17,000. So we can see a little better. Same idea, right? It grows and then it levels off. Because at some point, population doesn't level off. So it kind of grows and then levels off. It's a logistic function. What's the horizontal asymptote? As always, this right there. Y equals 16,500. The y equals is very, very important. It's an equation. So that should be y equals. What's the max population? That should just be the number. 16,500 foxes. When the population reached 16,450. Again, we already have the graph of this. This is y1. Let's type that in as y2. See where they cross. See what our answer is. So I'm gonna go y equals, go to y2, type in 16,450, hit graph. Then we're gonna find its intersection by going second, calculate intersection, hit enter, second curve yes, guess y of course, and then you get about 102.19. So 102.19, or about 120 years. There we go. That's the lesson.